Thank you. Hello and welcome everyone for this last talk. It's a machine learning pipeline as a language presentation. I am Berecz, a software engineer at Ekatel's data science team. In the data science team, the engineering group goal is to create a happy and carefree work environment for our data scientists. We try to achieve this by providing them tools that automate all the mundane and repetitive tasks. The main product of the developer group is the machine learning pipeline, which helps with the model training process, and it is the subject of this talk. So for a little context, let's check what is the life cycle of training a machine learning model is. So first, you have to start collect some data to train your model on. Unfortunately, in real life, this is often very noisy, so you have to do some data cleaning. After that comes probably the most creative part, when the data scientists try to come up with potential new features. When you have this, you can start the model training process, which starts with feature extraction, when you go from the raw clean data using the feature definition to the extracted vectorized version, which is compatible with your model input. Then you will do a train test split on this data. These are two distinct sets. You train on the train set and then you evaluate your model on the test set. You can do this in many various ways. For example, you can do a simply random split, 80% of the data you train on and you evaluate the model on the 20%. But you can do more sophisticated ones based on some metadata, like, for example, the transaction time. You evaluate your model on the last 3 months and you train on everything before that. Once you specify your evaluation setups, then you will have this iterative process when you are training a model, evaluating, and then setting the hyperparameters and choose what are the features that you want to use in the specific set. For an example, for hyperparameter tuning, in case for a very easy model for a decision tree, it will be like, for example, how deep your decision tree would be. When you do many iterations, you come up with your release candidate model, then you do some additional validation on this. These are mostly checks that the model behaves exactly the same way in production that it did in your training environment. Once all the checks are green and every sign-off is there, then you can deploy your model, and hopefully you have some model monitoring in place that can check the behavior of the model in production. So our machine learning pipeline takes care of this middle layer, so from feature extraction to the model validation. And when we were designing a system to tackle this, we were easy to find some pressure points that we really have to take care of. First of all is that for a single model release, we do 20 plus different type of train test splits, so a lot of evaluation, and we have like almost 200 different hyperparameter and feature selection. So you probably want to do this in parallel. Doing all the experiments in parallel or like almost all of them, because they are mostly independent, is very important. The other thing is that if you see this very high-level overview, is that you can have a chance to share a lot of data, intermediate data. Like, you only want to do the feature extraction once. You don't want to redo it for all the different train test splits. Once you have the train test split, you don't want to redo this split for all the different hyperparameters, because it can be reused. So parallelization and data sharing was two very main concerns, but this leads to very complex data flows, even if you just have this very simple view. And unfortunately, this simple view is exactly that, oversimplified. We have much more complex data flows, for example, in the feature extraction. Well, maybe not like that, because if you have really just simple feature definitions, then yeah, from raw data, you go to the extracted data, and everyone is happy. Complex cases can arise, however, when you have things like model assembly. This is the case when the input of a model is when the output of a model is the input for the other one. So you try to combine your models, then you will come up with something like this. And now you have to take care of parallelization and data sharing within this complex setup. However, my manager said that our company, we don't have problems, we have opportunities. So we identified these opportunities that we have to take care of. We have pretty complex data flow. We have to take care of internal and external data sharing, so between a single run and between multiple runs. And these little boxes have to be reusable in ad hoc experiments. A good example for this is that even though most of the model metrics have a proper mathematical definition, different implementation has little different things. And you want to be very sure that if the AUC is better for this model, it is really better. So, for example, you want to use one single implementation for metrics calculation, and you don't want to do it with different libraries. So you want to pick random elements from this machine learning pipeline and reuse in ad hoc experiments. So what we realized that for a single system to tackle all of this problem, it's just too much. We can't really take care of everything properly. And that's when we went back for a very basic but very good principle, which is separation of concerns. And we made the reality of this with creating a domain-specific language which tackles just a single problem of describing the data flow. We want to have a readable data flow so that the data scientists can write themselves, and if we write them, that they can approve it, that yes, this is what they want to achieve. And so some properties of this DSL is that we are creating serializable programs with it. There are no side effects during construction, so we are just describing what will be executed, and it can have arbitrary granularity. So the size of the building blocks can go from real small one, like a simple select, to more complex one, like calculating multiple metrics. And once we have our language, then we can have interpreters for optimization and execution. So then we can have separate interpreters. For example, Subtree Sharing, that we want to calculate everything once. We can have pruning to reuse already calculated intermediate data. And of course, we can have multiple execution interpreters for different environments. So let's start with this talk with describing the DSL. It is called pipeline program of A. The generic type A is, of course, the value you get if you evaluate this program. So yeah, it's a little bit long, so you should probably go with 0 on the naming, unless, of course, if the metric for your company is that how much character you type, because then go by it. So we have this sealed abstract class pipeline program. And then we want to have, of course, constructors to create this pipeline program. However, you want to keep the number of constructors low because you have to take care of every single different one in your interpreters, and you want to be scalable in that way. So let's see what we come up with. Of course, we have the classic wrapper that just wraps a constant value in our pipeline program context. We have read data. We are data engineers, so we probably need to read data. There is a read byte variant of this. And what you can see in the types that it is a pipeline program dataset. This is not some generic dataset. This is specific for Spark. We only use Spark, and we decided to just lock in and don't generalize over this. Of course, if you want, you can use things like Apache Beam, which is generalized over this, or you can write your own. So now we can create pipeline programs, and let's see how we can combine them. we identified two use cases. One is the both, which just takes a pipeline program A, pipeline program B, and then creates a tuple from them. And all, which has a list of pipeline programs, and it will create a pipeline program of list of A. But of course, the interesting part is how do you go from pipeline program A to B? And for that, we will need two things. The first is a transformer, which is very creative. You have an in and an out type parameter, and the function that will go from in to out. However, this has nothing to do with our pipeline program. The constructor is a transform, which takes two parameters, a transformer, which describes how to go from in to out, and an input, which is actually a pipeline program of in, and the type will be pipeline program out. So with that, let's see how we can write a simple program in our DSL, and hopefully demonstrate that it's actually easy to pick up. So, is it readable or? Okay, so first we start with a feature descriptor. We read an artifact in. In our case, the feature descriptor is called feature chain, nothing extra. We read in the data from our path. Then the features will be the extract features on this data using our feature descriptor. We have to create some metadata for evaluation and do the more sophisticated splits. We have to specify what is the target label for our machine learning model, and we have to add the metadata. Now that we have the features and the metadata, we want to join these two data sets and then select the columns that we are actually interested in, and we will call this preprocessed data because we also vectorize them and save it, which is what checkpoint data does. Now we define that what kind of evaluation we want to do in this case, and this is like a simple percent split where the trained data will take 80% of all. So the trained data is just on the preprocessed, call create trained data with the percent split, and the test data is the same, just call create test data. Now our machine learning model will be like on the trained data, train our scorer, and then please save it to the percent split model. And once we have our model, on the test data, we can score it with the model and then save it, so we can evaluate it separately. So this is just a description of this pipeline program, dataset predicted, and then we will execute it. So this is the domain-specific language. This is how you can write programs with it. And this execute is what will actually interpret this. One of our interpreters is called dot interpreter, which creates a visualizable version of this whole data flow, so we can check our transformations and blocks and what actually is going to be executed if we want it to. So let's check that. And what we see here is that, like a broken record, we are doing the same things over and over. We are reading in the data and the feature description, but 3 times. And we are doing everything 3 times. And you might ask why. And for this, we have to go back to our code. So when I said that with the DSL, we are only taking care of having a readable data flow and nothing with optimization, we took it pretty seriously, so there is really nothing optimized here. The problem is that, for example, at preprocessed is all the transformation leading up to preprocessed, and then we call create trained data, and that will be trained data. However, test data also have the preprocessed and all the steps leading up to preprocessed, and then calling a different transformation on that. And now we will do all the steps up to the preprocessed 2 times because they are present both in trained data creation and test data creation. So if we want to eliminate this, we somehow have to identify subtrees that are identical. And for this, we extended our DSL with our own hashing so that we can identify subtrees. And however, for this hashing to work, we needed some axioms, needed some assumptions that must be true for this to work. First, the data must be immutable, which is not a really controversial thing to say at a functional conference. However, it must be held true for all your data on S3, GCP, everywhere else in the cloud or locally. The transformers have to be deterministic, so if you have the same input, the same transformer, the output have to be the same. And also we are prioritizing safety over performance, so different programs always have different hash. However, for same programs, this is a best effort. For example, the best use case for this is the immutable data. If we have the same data under different path, we will say that the whole program is different because that's what we are. That's the path is identifying the data, and we are not checking the data itself for this. So let's see how this hashing then implemented for the constructors. For the const, it's pretty easy. We just take the JVM hash value of A, and then read data is just the hash of the path, which for the string is consistent between runs. So, but again, data have to be immutable for this to work. The interesting part is how we do this with the transformers. So for the transform, it's easy because it's just the hash of the input and the hash of the transformer. But the transformer is a little bit tricky. It has three parts: the constructor name, a version parameter, and the params. So the constructor name is the name of the actual transformer, for example, create terrain data or terrain scorer. The version is our implementation on how to take care of what is inside the apply method, what is the actual logic. So you can try and replace this manual versioning with something like hashing the bytecode that's generated, but then that will be sensitive for rewrites. And so we just go with, we are very careful with versions, and we always increment it when we are doing something that actually changes the logic in the apply. And you also have the parameters of the exact instance for the train scorer. This could be, for example, in the case of train scorer, this could be the hyperparameters, for example. So now we know how to identify subtrees in our DAG. So let's see what is the algorithm behind actually sharing these subtrees. So this is the easy use case. We can clearly see that the first three blocks should be shared between the two parts. And what we want to achieve is something like this. Unfortunately, we don't have yet introduced anything within our DSL that can take care of it. And so for that, we will introduce two additional blocks, ref and share nodes. And what we do is we basically split our original DAG to two separate parts. First, everything leading up to the subtree we want to be shared to a share node, and then replacing everything in the original program with reference node. And you can see this works through the hashes. So we will end the share and saying what is the hash leading up to this point, and the reference nodes will refer to this hash. But now we have two DAGs. How can we unite them? And for that, we just simply use a both case. So on the one side of the both, we will have our subtree leading up to the share, and on the right side, we will have the program where everything is where the appropriate subtrees are replaced with the reference nodes. The next thing that we want to improve is the pruning. So if we have this same data flow and we have a save part there, then we can say that, okay, there is a chance that this have been already calculated by a different pipeline. So we should check that if there is an intermediate data, and it's pretty straightforward. We will just replace everything leading up to the save point with a read node. Nothing to see here. Unless you see that the read node is still referencing the hash. So it tried to read what is under this 42FGH path. And yeah, so when we are, I was cheating a little bit. So you don't actually say that where do you checkpoint the data. You don't add the path that, okay, I want to save this data here, because that's automatically done by the DSL, that we will save the data under its node hash. And that's a problem, because when you end the run and you have like 600 outputs, and we have that for an average run, then you will have 600 random hashes, and you will have to somehow find where is that the actual model that you are looking for, or the actual evaluation, actual metrics that you want to check. And for this, we did an addition to our DSL once again. And this is tagging. So we can annotate our pipeline program. This is a metadata, which is just simply a map with tag key and string. We introduced tag key. We are still on Scala 2, so it's the old way of creating an enumeration. This is only to help us that we know that, okay, what are the possible values for the tag key, and the value can be any kind of string. So how does this work? How can we use this when writing our program? Yes, this specific example is really intrusive, but in practice, we don't have to do like this small chunk, don't have to tag this small chunk of data, so it's not that, it doesn't really affect the readability. So we have our read data, and now we put everything in a tag block where we says that the evaluation is the percent split and the model name is baseline. And then this report is the AUC. So on the score data, we calculate the AUC and checkpoint it. And then we also want to calculate the accuracy. So again, on the score data, we calculate the accuracy and save it. And as you can see here, these tags are adding in. So these outer tags will be applied for everything in between, but the tag report AUC will only apply that what is within its block. The output for this is a descriptor file, which looks like this. So we can see that the action is right, the data type is a data set, and the path is under this specific hash. And here we see the tags, the output type data frame, the eval is percent split, the model name is baseline. And what we have to be really careful when writing our exact pipelines, that all of the outputs can be identified with the set of tags. So we don't have two different outputs with the same tags, because then you can't identify them. There is only unit tests for this, nothing baked into the language that enforce you to have this property. And with that, I would like to thank you for joining me for this last presentation.